At this point in the year, you can tell me a great deal of information about right triangles. If I were to draw an arbitrary right triangle and label the vertices A, B, C, and the corresponding sides little a, little b, and little c, I think you would quickly tell me that the square of the hypotenuse is equal to the sum of the squares of the legs. You might also tell me that the sine of angle B is equal to B over C, that the cosine of angle B is equal to A over C, and the tangent of angle B is equal to B over A. You could probably tell me a heck of a lot more than that, but those are really the basics that probably pop into your head right away. This next unit is actually all about non-right triangles and figuring out what the properties of non-right triangles are. How are they similar and how are they different than these ones that we've already established? So the first thing that you should know is non-right triangles are often referred to as oblique triangles. Oblique triangles are really split into two cases. There's the case where you have three acute angles, like an equilateral triangle, for example, or a triangle with a 80-degree angle, a 40-degree angle, and a 60-degree angle. And then there's also oblique triangles where there is one obtuse angle, and then the other two are acute. Of course, any triangle can't have two obtuse angles because they would add up to more than 180 degrees all on their own. So this next unit's all about these oblique triangles, and oblique triangles, the conversation really begins with something called the law of sines. So that's what we're going to get into in this video, and I'll start to explain that right with an example here. So in our very first example, let's just say you, put a capital Y here to represent you. Just say you're hanging out with your friend Zev, and here's Zev with a capital Z. And because of the times that we're in, you're maintaining social distancing, and let's just say you're 8 feet apart, more than the recommended 6 feet apart. And everything's going along well. You and Zev are having a nice little conversation when all of a sudden here comes person X. Maybe it's Xavier or Xander or somebody like that. And you're wondering, is this person X, are they infringing upon your space? Are they crowding your conversation? Are they closer than 6 feet? So we would like to know, what's the distance between X and Y? What's the distance between X and Z? So rather than measuring the distance, since you and Zev are both trig students, what you do is you measure the angle between person X and Zev, and you find that that angle is 60 degrees. And then Zev does the same, and he comes up with 45 degrees. So this is the information that we have, and this is enough to tell us that we do have an oblique triangle. There's no right angle here. And what we'd like to know is we would like to know what is the length of xy and what is the length of xz. So I'll label those with little z and little y, respectively. I use little y for the segment xz because it's across from angle y, and then I use little z because it's across from angle z. It's a nice way to not have to use too many variables and to keep everything nice and organized. Okay, so this is a new problem because we don't have any right angles. So the natural thing to do is to create a familiar situation. One way you can create a familiar situation in this case is to drop an altitude from vertex x. Now I have right triangles. That altitude, that altitude, I'll call that h. And what I can say right away now is, looking at my two right triangles that I've formed, I could look at the sine of angle y, which is the sine of 60 degrees. And I can say that that is equal to h over z, because the sine ratio works in a right triangle, and I have a right triangle there. Meanwhile, looking at the triangle on the right-hand side, I could say that the sine of 45, which is the sine of angle z, is equal to h over y. Okay, that kind of gives me an idea. If those two things are both true, then I can solve for h in both of those problems. I can say that h is z times the sine of 60, and I can say that h is equal to y times the sine of 45. And of course, that means that z sine of 60 is equal to y sine of 45. And if I just follow this thought process all the way through, what that means then is the ratio of y to z, something about dividing both sides by z here, is equal to the sine of 60 divided by the sine of 45. And that is a very, very interesting result. If we just look at that kind of color-coded here, I think it helps. Sine of 60, well, that was angle y, and it corresponds proportionally to side y. And sine of 45, that was the sine of z, and that corresponds proportionally to the sine of z. So what we have here is we've come up with not exactly what y and z are equal to yet, but we figured out that the ratio between y and z is equal to the ratio of the sines of angle y and the sine of angle z. So that gives me another idea, maybe an idea that will tell me what y and z actually are. So I'm going to go back to my diagram here for a second, and I'm going to get rid of my altitude that I drew from x, and instead, what I'm going to do here is I'm going to draw a different altitude. This time I'm going to draw an altitude from vertex y, because why not? I'll just draw that right there. Boop. Perpendicular to xz, and I'll call that, I'll just call that h again. I'll call it h2. It's not necessarily the same height as h was. So now what I'm looking at are two completely different right triangles, and I want to see if I get the same result. So let's find out. If I look at the sine of 45 here, the sine of 45 degrees, that's the sine of z, that is going to be equal to h over 8, because it's the hypotenuse of that triangle there is going to be that 8 feet right there. Okay, and then if I look at the sine of angle x, okay, we haven't talked about angle x here, but we actually know exactly how big angle x is. Angle x, you can't hide a single angle in a triangle. If y is 60 and z is 45, that adds up to 105, and that leaves exactly 75 degrees for angle x. So I can now say that the sine of 75 is equal to h, and oh, this is h2, I should call this h2 over z. So what that means now, if I follow the exact same thought process that I had before, was that h2 is 8 sine 45, and h2 is also z sine of, let me just write that a little nicer, out of space here, z, nope, don't want the eraser, z sine of 75. So that means 8 sine 45 is equal to z sine 75, and now I've got the exact same proportionality that I had before. Sine of 45 divided by sine of 75, which is the ratio of the sines of the two angles, is equal to 8 over z. Z over 8. I got that backwards there. Z over 8. And that's enough information to solve for z. In fact, I could just kind of punch it into my calculator here, and I could say that z is equal to 8 sine 45 over sine 75. Making sure you're in degree mode. You will get that z is equal to 5.8, 5.86. So person X right here came a little bit too close to you. That's no good. But what the bigger point is there is that we actually figured out some new information that we can use now in a very, very efficient way to solve oblique triangles. So let's talk about a proof of that so we can see how to make it more efficient. This would be our proof. And this is a proof of what we call the law of sines. Okay, so here's an x, doesn't have to be anyone in particular, and here's a y, and here's a z. Yep, just like that. All right, and here's little x, and here's little y, and here's little z. Okay, so now I come along and I draw my altitude, and I call that altitude h. Okay, and then I say, all right, I got a right triangle, so I can say that the sine of angle x is equal to h over y. And then looking at the triangle on the right-hand side, I can say that the sine of angle y is equal to h over x. And that means y equals, keep goofing up here. That means h equals y sine x. And it also means h equals x sine y. And that means y sine x equals x sine y. And that, of course, means sine of x divided by x is equal to sine of y divided by y. Just like that. And, of course, there was nothing special about this particular altitude that I drew. I could have drawn an altitude coming from vertex x. And I could have wrote the same exact ratio, but now z would be involved. So I would be drawing the conclusion in that case that the sine of y over y is equal to the sine of z over z. And that there is called the law of sines. Okay, so let's see an example. This is example 2, using the law of sines. Okay, let's say I have a triangle here. And let's just say I have a 91 degree angle. Now I know automatically this is an obtuse triangle. And let's say I have a side across from it that's 7 units long. And I'm going to give you one more piece of information about this triangle. Let's just say I tell you this side right here. Now, it's obviously not going to be 0. That wouldn't be a triangle. But in that circle, I'm going to put the side length. The other piece of information, let's just talk about what kind of number I could put in that circle. Since 91 right here is my obtuse angle, and I can only have one, and because the side across from the largest angle has to be the largest side in the triangle, I better put a number in that circle that is smaller than 7. All right, so let's just say I go with a 5. Okay, so there's a 5 and a 7, and I get a 91. And I want to solve this with the law of sines. So the first thing that you do is you just find an angle side pair. That's how you know the law of sines is going to work. So you see it right up here. Sine of x over x means I have to have an angle side pair. So I can write the ratio sine of 91 degrees over 7 is going to equal, okay, now I better put a variable or two. Let's just label the triangle A, B, C. So what I just filled out there was sine of B over B. And now what I would do is I'd say, all right, I'm going to use this 5 here. So across from the 5 is angle A. So I'll say, all right, how about sine of A over 5? And I want to solve this for angle A. That's what I'd like to work that out. Once I work that out, I can kind of go through and work everything else out in the triangle. So, okay, let's do that. So to solve for angle A, first I'll have to solve for the sine of A, and the sine of A is going to be equal to 5 times sine of 91 over 7, and that means angle A is going to be equal to sine inverse of this big mess that we have right here. And don't fret, we're not going to be working that out without a calculator. So we punch that into our calculator. Sine inverse of 5 times sine 91 divided by 7. And I find out that angle A is equal to 45.6 degrees. 45. Make sure you're in degree mode. Wouldn't want to work this out in radians. So now I know angle A is equal to 45.6 degrees. Now, one thing that I wanted to point out, if I had made a bad choice here for the missing side, if I didn't choose wisely, if I say I made that an 8 instead of a 5, an 8 would be a bad choice. What would have happened down here, I would have gotten not 5 times sine of 91, but I would have gotten 8 times sine of 91 over 7. And it just so happens that 8 times sine of 91 is bigger than 7. So when we divide by 7, we get a number that would be larger than 1, and we know that the domain of inverse sine is from -1 to 1. So we need to make sure that our input is in that range, and as long as you come up with a reasonable triangle, that will be the case. Okay, so what now? I worked out angle A. Now I could quickly figure out angle C using the fact that there's 180 degrees in a triangle, and 91 plus 45.6 is 136.6, and if I take that away from 180, I work out that angle C is 43.4 degrees. And the only thing that's left to do then, if I figured out angle A and angle C, the only thing left to do is to figure out side C, which would be this side right over here. And, you know, I already know that this side right here is smaller than 7 because angle C is less than 91, and it's smaller than 5 because 43.4 is less than 45.6. But I could figure it out exactly. I just go back and I use law of sines one more time. So let me just kind of erase my work up here. Give myself a little more room to work. And I would say, okay, sine of 91 over 7, I'd still use that angle side pair. Using the given information is always a nice idea. Is now going to be equal to the sine of angle C, which was 43.4 over side C. And that means that side C is going to be equal to 7 times the sine of 43.4 divided by the sine of 91. And when you work that out, you get that side C is equal to 4.8, a little bit smaller than 5 as we anticipated. So that's how you use law of sines.